Hi everyone, we're going to be doing our last unit today, which is on phase, equilibrium, and solutions. So a rough breakdown of contents is there. To begin with, we're just going to review the concept of phases. Normally we talk about phases as being solids, liquids, or gases. It's a phase is basically a part of a system that is physically homogeneous within itself and separated by a definite boundary from some other phase. So ice and water in the example here, or also you see in this picture the air and the water, there'd be a definite boundary between them as well, separating those two phases. Gases have complete freedom of motion. The particles are free to move relative to each other. They'll fill a container, they'll flow. They're very compressible as well. So what this means is if you mix any two samples of gases together, the particles will sort of freely intermingle like you see in the picture here. So you can't have phase boundaries with gases. For liquids, the particles are all packed together. They're all more or less in contact, even though they're still able to move and flow relative to each other. They're essentially incompressible, meaning if you put pressure on them, the volume doesn't change by very much at all. And that's because there's really not a lot of empty space that you can kind of compress the atoms and molecules into. So liquids can form multiple phases and have definite boundaries between them. So the example we see here is on the right, a mixture of water on the bottom and vegetable oil on the top. These will form two distinct phases with a distinct phase boundary in between them. So some terminology here before we get too far in. If two liquids are mixed together and form a single phase, and there's no phase boundaries, we would say that those two liquids are miscible in each other. And if they do not mix, if they form multiple phases like the oil and water, we would call them immiscible. So mixtures that are maybe one phase under a given set of conditions, but maybe multiple phases if you change the conditions, for example, changing temperature, we might call those partially miscible. This is just a neat little demo of an experiment where what we have here on the top is vegetable oil. Well, I guess that's written right there. You don't need me to draw another arrow. On the bottom, we have blue food coloring and water. So there's sort of a phase boundary that exists right there. And then what you can do is drop an Alka-Seltzer tablet in. Alka-Seltzer has dried sodium carbonate and citric acid, basically the same two substances that you'd find in a bath bomb. When those are wetted, they will react with each other according to this reaction to produce CO2 gas. And so the gas bubbles are going up and dragging some of the water with it. And so you can see definitely the phase boundaries between the little droplets of water in the oil. Solids are, the particles are all packed together very tightly. They're not able to move relative to each other. There's no flowing in a solid. There's still some motion, and you can see in my little picture right there that there's some vibrational motion going on with those atoms. They're kind of jiggling around in place. But solids themselves, aren't able to flow like liquids and gases. Solids can exist in more than one phase for the exact same material as well, and we call these things polymorphs. So an example you sometimes see within a single sample, multiple crystal structures of a single material. So allotropes is basically the word that we use to describe pure elements that exist in different physical forms or different crystal structures if they're solids. Example with carbon would be something like diamond and graphite are the two most common ones. There's fullerenes, which are things like C60 or a buckyball, and nanotubes and things like this. These are all pure carbon atoms, but different physical forms or different sort of structures at the molecular level. These are different allotropes of white phosphorus and of phosphorus, meaning phosphorus can exist in a number of different structures for the same pure element. We have white phosphorus, which is P4, which has this sort of tetrahedron shape. Red phosphorus is shown here, and black phosphorus over here as well. This is another neat little demonstration where white phosphorus, if you dissolve it in something that is volatile, you can sort of draw with it once the solvent has finished evaporating away and the phosphorus is exposed to the air, it will spontaneously ignite, and you can see that in the little image below. Okay, so if we have vapor molecules, or any liquid really, at the boundary between a liquid and air, which I've sort of pointed to right here, you can have evaporation of the liquid up into the air, or you can actually have deposition of gas molecules in the air back down into the liquid itself. But our experience is more that things will evaporate away. If you had a beaker like you see here full of water and you left it open for a number of days, eventually all of the molecules would evaporate out of solution, would dry up, for example, and then they'd become gas phase molecules. If we were to sort of put a cover on top of here, if we could seal the top, what would happen is some of the water would evaporate into the kind of headspace that you see above the surface of the liquid, but because those can't escape, you'll only evaporate a certain amount. And so that amount of gas that will evaporate in a closed container is known as the vapor pressure of that liquid. And the vapor pressure will change depending on the temperature, depending on the nature of the liquid, but at a given temperature, the vapor pressure of a particular liquid is going to be a characteristic value. So we call this PVAP. That just means the vapor pressure of a liquid. Things that have high vapor pressures, basically these are things that evaporate quite easily, and we use the word volatile in chemistry to describe liquids that have high vapor pressures or liquids that evaporate easily at sort of ordinary temperatures. Things like hydrocarbons, like gasoline, things like nail polish remover, which is usually either acetone or ethyl acetate, or a mix of the two, and really any other kind of liquids that easily undergo evaporation. Eventually what's going to happen in this closed container you see on the right is we are having evaporation take place from the water molecules in solution. So you can almost write that as H2O liquid going to H2O gas. And this will continue to evaporate until the vapor pressure has reached a point where you cannot really get more gas into the gas phase. And what's happening at the same time as evaporation is some of the water molecules are coming down and colliding with the surface of the water and re-entering the liquid phase as well. So this reaction is reversible. At the point where the rate of evaporation equals the rate of re-entering the solution, we would say that that would be an equilibrium situation when those two rates are the same. And the pressure that exists when this has reached equilibrium is the equilibrium vapor pressure, which is a characteristic value for particular substances. So we say ordinary evaporation is a surface phenomenon, which basically means the water molecules that are entering the gas phase must enter the gas phase from the very surface of the water. You don't have molecules from deep within the liquid suddenly rushing through all of the solution and going into the gas phase. Just the ones that are on the surface can. If you go to higher temperatures, though, more molecules will have enough energy to vaporize, and what can happen is you get pockets of gas that can form within the solution, not necessarily at the top, not necessarily at the surface. and so that's typically what we would call boiling. Solids can also have a vapor pressure. Typically they're much lower, typically because intermolecular forces are stronger for solids than they are for liquids, but you can still have a solid lose material through loss of atoms into the vapor phase as well. We call this sublimation, and you can see this if you ever tried to make snowballs and store them in the freezer for very long, or for that matter, if you even make ice cubes in an open ice cube tray in the freezer and leave them there for a long time, slowly the ice in the ice cubes will get smaller and smaller and eventually all enter the gas phase. This is a pretty sweet freezer, by the way. They've got Eggos and M&M's ice cream, so hey, it's not too bad. So vapor pressure and boiling. The boiling point is defined as the point or temperature where the vapor pressure of the liquid is equal to the external pressure. So the boiling point of a liquid will change depending on what the external pressure would be. Because pressure decreases when you go up in altitude, boiling points decrease when you go higher up. The normal boiling point, though, if you put normal in front of the word, that signifies that the atmospheric pressure or the external pressure is 1 atmosphere. So at the boiling point, the normal boiling point we define as the point at which the vapor pressure of the liquid is equal to 1 atmosphere. It's funny that we use atmospheres here and not bar, because bar is the SI unit that has been adopted for almost everything else. But atmosphere remains for boiling points, probably because they didn't want to have to change the boiling point of water from 100 degrees Celsius to, I don't know, 100.5 or whatever it would turn out to be. So at the boiling point, remember when we're not at the boiling point, evaporation occurs from the surface, but when you are at the boiling point, you can actually see bubbles form from within the liquid and rise out. Just wanted to show you this picture. This is what a pot of water looks like when you first put it on the stove, and you can see all the little bubbles kind of all on the bottom here. This happens very soon after you start heating the water and when you're nowhere near the boiling point. Those bubbles are actually not water vapor. These are dissolved gases that are in the water that come out of solution when you start to heat the solution. And those form because as you heat a liquid like water, the solubility of most gases actually decreases. So this is things like nitrogen and oxygen coming out of the water. There's a quantitative relationship between vapor pressure and temperature, and it's given by the Clausius-Clapeyron equation, which you can see right here, where we have the two different temperatures. So basically what we can say is that the pressure at one given temperature, T1, is related to the pressure at a second temperature, T2, by this equation where R is the gas constant, 8.314 joules per k mole, and the delta H is the delta H of vaporization if it's a vaporization process that we're looking at, or sublimation if it's a sublimation process. And that's it. One thing we always have to keep in mind is that the units that we use always have to agree with each other. We can use any units of pressure for P1 and P2 as long as they're the same for P1 and P2, because units are going to cancel in this equation. Same with temperature. We can use, typically use Kelvin for temperature, but for delta H and R, delta H we often use kilojoules. We have to always convert this to joules per mole in order to match the 8.314 joules per k.